Alright, so in this particular video, I will show you how to find the angular momentum of a point mass when you're given information in the IJK notation. So for this particular example, we have a mass of 2 kilograms. It is a distance away from the origin given as r equals I plus j, and your velocity vector is given as v equals 2 parentheses I minus j plus k close parentheses. So part A asks us to determine the angular momentum about the origin. So here is a diagram just to help you visualize what's going on. Here O is for the origin. This is your position vector r, and blue is your velocity vector, or it can also be treated as your momentum vector. Keep in mind, your momentum and your velocity vector really lies in the same plane. And the only difference is that momentum has a coefficient in front of v because it has some mass. Okay. Other than that, I'll help you find part A, and then from part A, you can extract the information or the answer for part B pretty quickly. All right, so let's go ahead and do it. So for these types of problem, you want to go ahead and start with this particular variation of angular momentum, L equals CR cross P. You want to use this format because it is a point mass moving in a plane. It is not a shape rotating around a pivot. Okay. All right. So other than that, hopefully you know that C is a 1 for these types of problem because the coefficient of a point mass during your moment of inertia topic or unit is a 1. Again, C here is a 1 because the coefficient of a point mass is just a 1. So we can go ahead and eliminate C for these types of problem. So really the only two things we need is R and P. But R is given to us as I plus J. So the only thing we have to find is P. But to calculate linear momentum, it's pretty straightforward. Linear momentum is just mass times velocity, which are both given to us in this particular problem, where mass is 2 and the velocity vector is given as 2i minus 2j plus k. So if we want, we'll go ahead and distribute the 2 to the coefficient in front of the velocity vector. So 2 times 2 is 4. 4 times I is 4i. 4 times negative 4j is negative 4j. And then 4 times k is 4k. So there is your linear momentum vector, 4i minus 4j plus 4k. And then I'll go ahead and put these two vectors over in the diagram here just to help you visualize. So again, here we have r, I, and j. There's no k, but for linear momentum, we have I, j, and k. So let's go ahead and take the cross product. Again, to find the angular momentum for these types of problem when information given in the form of ijk, you do have to take the cross product of r and p. The coefficient again for c is just a 1. So let's go ahead and take the cross product of r and p. R is rx, ry, rz in this particular format, and then there's px, py, pz. The information for r, x, r, y, r, z can be extracted from the position vector given. The coefficient in front of I is a 1. The coefficient in front of j is a 1. And there is no k. So the coefficients are just 1, 1, and 0. And likewise, you can pull the same information out looking at the linear momentum vector. This is 4i minus 4j plus 4k. The coefficient in front of I is 4. The coefficient in front of j is a negative 4. Don't forget to include that negative sign. And then the coefficient in front of k is just a 4. So that's where all these values are from, 4, negative 4, and 4. And therefore, let's take the cross product. If you don't know how to take the cross product, please watch a separate video on how to take the cross product, and then hopefully this will make more sense. Okay, so to find the I vector, we would just have to take a j cross k. So you notice here in my work, I block out I because I'm trying to find I. So all I have to do is cross j and k to get that particular vector. So this information is carried down here. And then next to find j, we would subtract the next set of work. So you would visually block out j. You need to keep I and k. So when you take the cross product, if you take I cross k, you get j, whether it's positive or negative. That depends on the direction of motion. Okay. Other than that, you would subtract the next work here. And then last but not least, to find the k vector, you would cross I and j. So all this right here is carried down here. Keep in mind, this is the general format for a cross product. You would minus and then plus. All right, so if you do it in the same order, I, J, and K, these are your symbols, minus and plus. All right, and then on the right side of the equal sign, these values come from the right side of here. Again, Everything is labeled in order for you: R, X, R, Y, R, Z. So if you keep in mind, this first chart where my cursor is R, Y, R, Z, and that is given as 1 and 0 here in the chart. Okay, again, R, Y is a 1, R, Z is a 0, and that's where the 1 and 0 comes from. And then the negative 4 and 4 comes from PY. PY in this case is the middle term there, that's negative 4. PZ is this 4. So that is your first set, minus your second set of data. And that is from I and K. So RX is 1, RZ is 0. That's where the 1 and 0 comes from. And then to find PX and PZ, again, PX in the same order, this is a 4 and PZ is also a 4. So that's where the 4 and 4 comes from. And you can do the same for the last piece of information here for the K component. All right. Other than that, we just do the cross product literally by taking 1 times 4, which is down here, 1 times 4. We would subtract 0 times negative 4. I wrote that just for you to see, but 0 times anything is just 0. And then subtract the next term, and that would come on the screen here. That would be 1 times 4. This is 1 times 4. That's the first term in the second set of data. 1 times 4 minus, and then you would do 0 times 4, which is going to come up on the screen here. And that would represent this work right here. And then last but not least, we have 1 cross negative 4, and then 1 times 4. So 1 times negative 4 is a negative 4. Subtract 1 times 4, which is 4. So if you do your reduction carefully, you should get this particular outcome. Okay, so watch my cursor. 1 times 4 is 4, minus 0 is just 4, and then minus, again, 1 times 4 is just 4, minus 0 times 4 is just a 0, so that minus sign is right there, and the answer in the middle term is a 4. And then this last term here is a negative because while this is a plus sign on the outside, 1 times negative 4 is negative 4. And then negative 4 minus another 4 is a negative 8. So you can express plus 8, or excuse me, plus negative 8, or you can just express as a negative 8. Okay. Other than that, that is your answer for part A. Excuse me. Now, to find the answer for part B just asks us for the angular momentum about the z-axis. So really all we have to do is that right there. So the answer would simply be just negative 8k, because that is the angular momentum in the z-axis. In this case, z is your k because it's x, y, z, I, j, k. So it follows that order. So the answer would just be negative 8k. All right. Let's move on to the next example. All right, so here we have a similar type of problem where you have a particle moving in a plane. The velocity vector is given as 2i plus 3j. Again, notice here there's no k component. And then it asks us to find angular momentum where the particle is about the origin when it is at 1, 1, 0. So if you think about it, this 1, 1, 0 really is your r, your position vector coordinate. Okay. So we would start with the same starting point. Again, in this case, we want to go with this strategy. We equals C times R cross P for these types of point mass system. Okay. R vector, we can extract from the set of parentheses in the given statement. It's 1, 1, 0. So really it translates to I plus J, and there's no K because there's a 0. Other than that, to find P, we employ the same strategy as previously found in the first example. To find linear momentum, we take mass times velocity. In this case, the mass is 2 again. Your velocity vector is in blue, and that is given as 2i plus 3j. And from here, we just distribute again the 2 to the 2 and the 2 to the 3. So that will yield a linear momentum of 4i plus 6j. All right, and then now we just take the cross product again. So if you kept up with the last example, set this table up, whereas in the exact order R, X, R, Y, R, Z, it follows I, J, K, and then P, X, P, Y, P, Z. And then the information to the right of the equal sign here can be extracted from your position vector. Again, the coordinate system here is given as 1, 1, 0. That's where the 1, 1, 0 comes from. And then the 4, 6, 0 comes from your linear momentum vector. So where my cursor is, that is a 4, and that follows under I, and that's I, and that's the 4. Then J here is a 6. So under J, we put a 6. And then again, notice there's no K component in this case. So we would just put a 0 as a placeholder. So I hope you notice here in this particular problem, excuse me, under k, you have a 0 and a 0. And this will make a bit more sense, hopefully, in the next strategy on how to solve this problem. Okay. Other than that, let's go ahead and block out I. In order to find vector I, we take j cross k, and that leaves us with this. And then we will subtract the next cross product to find j. To take j, you would take I cross j, cross k, excuse me. So to find j, you take I cross k. Again, that leaves you with rx, rz, px, pz in this next term. And then last but not least, we would add the last cross product. And then the last cross product would require you to take I cross j to find k. And then all this that's left over here that hasn't been blocked out would just be carried down here. And then again, everything is in the same order. So here it's just plug and chug. Okay. Ry, again, is in the middle. That's a 1. And then Rz is a 0. And then Py is a 6 because that comes from that table there. And then Pz, which is 0. And subtract. And then this is 1 from Rx. Rx here is 1. And then Rz is a 0. This is Rz. And then Px is a 4 because Px is the first term there, and that's a 4. We carry that down. And then Pz is the last term, which is a 0 right there. And then we carry that down. And then you can do this last piece on your own. Excuse me. And then the format, again, to cross multiply, it'd be 1 times 0 minus 0 times 6 minus 1 times 0 minus 0 times 4, and then plus 1 times 6, and then minus 1 times 4. So the work is going to look like this. If you just plug all the values in where they need to go, Ry would be 1 times 0. That's right there. Minus Rz, which is 0, times Py, which is 6. Okay. And then you can do the same for the rest of the stuff. So notice here, 1 times 0 is just 0, minus 0 times 6 would just be 0 anyways. So there's no I component. And then here, 1 times 0 minus 0 times 4. This whole set in the middle also gives you a 0 because there's nothing here. 0 times 1 is 0, and then subtract 0 times 4, which is 0. 0 minus 0 is just 0. And then really that only leaves us with the k component. 1 times 6, which is 6, minus 1 times 4, which is 4. So 6 minus 4 would just give us an answer of 2. Okay, so that is your overall outcome. I think the tricky part here is learning how to take the cross product, which can be a little messy if you don't follow. So if you need to play the video back and watch where everything falls in place. Really, you just have to line everything up. It's not too bad. All right, but here is a different way to look at that last particular problem. Okay, so unlike the first one, I noticed here right away there's no k component in the precision vector and also in the velocity vector. So here's just another way to look at it without doing all the confusing cross product stuff. So I would employ the same function, except here I notice that my p, it is a diagonal, so it has to have a px. And then px is just 4. If you take the mass, which is 2, and you times that by the velocity vector, which is 2I, which represents the information in the x direction. So 2 times 2 is 4. And then here you have a vertical component as well in the y direction, and this is py. But to do py, we would take mass times vy. Your mass here is 2, and your velocity vector component in the y direction is a 3. So 3 times 2 would just give you 6. So here you have a diagonal vector, and it has to have a velocity, a momentum component in the x direction, and then a momentum component in the y direction. And same goes with the position vector. Again, your position vector is given as 1, 1, 0. So if you look at my work here, Rx would just be 1. Why? Because it said so in the statement. And then Ry is also 1 meter. And that is your coordinate here. And that's X, Y, and Z, aka I, J, K. So Rx is 1, Ry is just 1. And then, so hopefully when you do angular momentum, you think of cross product, and cross product to me just means perpendicular. So I kind of move everything here for you to show you that if you just line things up, you need a P and an R that are perpendicular to each other. In this case, P is Py, so therefore you need a moment of arm in the x direction. So I just carry these visuals over. But as you can see here, here's the pivot where my cursor is, because that's the origin. So I kind of visualize Py, as a force. If you were to pull this vector up, it would rotate in the counterclockwise direction, uh, which comes up on the screen here. And then same thing here. I move the ry vector to the right side of the screen here, and then I move px. Again, x and y are perpendicular. So here's the pivot at the bottom of the ry vector, because that's where your origin is. And then if you were to quote unquote pull with the blue component there, it would rotate in the clockwise direction. So right away, I noticed that one is counterclockwise, one is clockwise. So you would just end up subtracting the two outcome. All right. So to do L, again, I left the C out because C is just a 1 for a point mass. You take R perpendicular to P. R in this case would just be 1. P would just be 6. 1 times 6 is just 6. And then for this one, we would do the same, where R, again, for this case, happens to be also 1. But the momentum in the x direction is a 4. And then 1 times 4 is 4. So therefore, the angular momentum rotating in the counterclockwise direction would be a 4. All right. So other than that, because they rotate in the opposite direction, or sometimes reference this as into the board and out of the board, or into the page and out of the page, uh, you would just subtract these two. You subtract because they are acting against, and then really the outcome would just be also a 2. So this is just a different perspective look at that last problem or the second example without doing the cross product. Okay, I hope that helps. Other than that, stay nerdy, don't be white.